Hello everyone, welcome back. So let's continue. In the last lecture, we have talked about whole flexures and we saw some examples. So how it can be implemented and we can get a different kind of flexure mechanisms. So we also discussed about this problem. So how to dimension. So we'll just go through again once again. So we have force affecting and then we have a displacement. So a straight guidance problem or a parallel guidance mechanism, what we can say here. So that's what we achieved. So just developed a CAD model and actually what we can see here that is a 3D printed and when you apply a force, you can see that you can see a displacement there over there. So very simple but very effective solution for any kind of movement, and if the range is limited to few millimeters, so it can be below millimeter also, and in many applications that may be enough, but even in the range of millimeters it can work really well. So we can look at it. So suppose if we have to design this kind of stages or flexure mechanism, so for instance this is what is required. So the displacement is 0.5 millimeter and some of the dimensions given like thickness, the diameter and the length of the link, effective length P, that is given. We have chosen the material for instance and this is also provided. So given these dimensions, what are the other dimensions missing? So for instance the H, the thickness of the hinge, and the other performance characteristics, for instance the stiffnesses. So we might be interested, and what I mentioned that we have the charts to use. So there is a non-dimensional parameters along y-axis, and then in x-axis we have under root h by d or h by d. So for most of the calculation it should be good enough, we can use it. But if we really want to know the numbers, yes, one thing we can always do is we can do the FE analysis. So we can check how close are these numbers, and of course with the experiments we can do model analysis, we can do the vibration analysis, and we can find what are the stiffnesses values. So this is what I mentioned last time. If we proceed, we should be able to arrive at these numbers. So close, not necessarily it has to be exact, but somewhere there. So I just worked it out so that you can also cross check. So for instance, this is known, the displacement, that is 0.5 millimeter is a given. So what is provided in the beginning is your sigma values and the E values given. So for that, this psi, the rotational, the deflection of the hinge, what is that? So from this excursion we can find, so we can use this formula, p psi equal to delta, and then we can calculate, and this is delta over p, and be careful about the units. So it should be the same units, and preferably many times we try to use SI units itself. So yes, mm, and okay, here it can get cancelled, so it's okay. Otherwise we can always write in terms of meters, and then we can cancel it. Also remember that the way this works, the angular deflection will be in radians, so be aware of that. So once we put the values 0.5 by 40, this is what we get. 0.0125 radian. So that we can put here. So sigma versus psi e, that's something we can obtain very easily. So sigma is a given, so it's a 400 megapascal, so 10 to the power 6, and then psi value in radian, and then e value again 10 to the power 9 because it's a 210 GPa. So we put, and then what we find that what we get is 0.152. Yes, so if we use the chart and check this corresponding plot, 0.15 is, so if we check this y-axis, so 0.5, so 0.1, 0.2, so somewhere in the middle, 0.15. And if we go here and check the orange one, so roughly, yes, here we are here, and we can say that, okay, for the 0.15 y value, that is for sigma by psi e, and corresponding to that, if we look at the chart for 0.15, what we are getting for under root h by d is a linear plot, so it's a better to use that. So we use that, and it's a 0.5 is here, and where what we can see 0.1, 0.2, and here this is 0.25. Yeah, somewhere there. So under root h by d is 0.25, and once we put the values, we can find h. So 0.25 square because it's under root h by d. So when we do a square, then h by d is equal to 0.25 square, and we take the denominator on the other side. So this is what we get, and when we multiply, it's in millimeters. So what we find is 0.62 millimeter. So be aware of the units. If we are writing in meters, then we should write in meters. But if it's in millimeter, then be aware of that. So 0.62, that is the thickness of the hinge. So if the whole the diameters are given, so this is what we are talking about. So this is the h. So we obtained, and this is one of the geometric parameter which was missing. So the thickness we got. Yes, we can also take lower values, but yes, for simplicity we continue with that, and if we take 0.62 millimeter, so we'll continue with the same h by d. So under root h by d is 0.25, and if we continue along the same line, what happens, we might be interested in knowing the k value, the stiffness, rotational stiffness of this hinge. So it will be, so we apply a moment and there will be deflection. So yes, the effective stiffness is the stiffness of the hinge. So then we use this plot. So first we use this plot to arrive at h. Once it's known, now we are interested in finding k psi value. So we use that plot, and if we extend, what we realize that this is 0.3. So this value, so we use 0.3 for that one, and when we substitute, yeah, so this 12k psi divided by ETH square, so it's 0.3. So similar, so if we just move other terms to other side, we should be able to find k psi, and that is 0.3 times ETH square by 12. So we can put the values. Again, be aware of this numbers, it's always better to use SI units. So for instance, for E 210, 10 to power 9. For T is millimeter, so 10 millimeter, 10 or 10 power minus 3. H is again 0.62 millimeter, so 0.62 square, and then mm is 10 power minus 3 square is 10 power minus 6. So 6, 3, yes, it's minus 9 plus 9, it will get cancelled, and we will be left with 0.3 times. Yes, here if we calculate, we will find 67.27, and if we plug these values, it's 20.18. Be aware of the unit is the for the hinge, so Newton meter per radian. So it's a SI unit, and we should be always aware of the units as an engineer, because yeah, if we are not working with the consistent units, we can have a serious problem. So be aware of that and always stick to SI units. Is known to everyone and everybody can interpret it well. So even if the units are not given in SI units, it's always better to convert into SI units and then use accordingly. So this is the stiffness of the hinge. The hinge, and particularly what we'll say rotational, and that's why unit will be moment Newton meter divided by the angular deflection, that is in radian. So as we move on, what we wanted to find is the stiffness, equivalent stiffness. So what is the stiffness in this direction? And what we realized that there are now hinge stiffness for four springs, what we can see, and because of that there will be certain stiffnesses K total in this direction F, and that we are interested in. So we can use energy equation. So half K total, that effective stiffness, and that is delta square, and that is stored in the potential energy is stored in the springs, individual springs. So there are four times half K psi square. So if we do that, so half get cancelled, and then K total will be, because all the four are acting in parallel, so it will be summed up. And what we see is here is the effective stiffness or the contribution of the the hinge stiffness towards the stiffness at F is actually K psi by P square. So P is the length. So and here delta psi by delta can be written in terms of P. So this is what I have done. So psi divided by P psi get cancelled. So we are left with 1 by P. So it's a P square. So this is just, I'm not cancelling 4, so I'm just keeping it, and then this is what you have. So once we put the value for P, this is what we have, K psi, right? Now always remember that this is the unit we are talking about, is the linear stiffness, and that's why now the unit is Newton per meter. That we can also check in the formulation. So P square is there, so meter square is there. So and for the K psi is Newton meter per radian. So meter will get cancelled and meter will come down. So that's why we have Newton per meter. So it's a consistent. We can also check using those dimensional units. So this is the overall stiffness. So if you want to calculate the force, so what is the actuator force or actuation force for that deflection, that delta deflection, which is 0.5 millimeter in this case. So we just plug that value, and then the actuation force will be 25.2 Newton. So yes, it's just to show how to calculate, how to arrive at these numbers, and it's a good way to also learn that how the things are placed, and you don't have to memorize the formulas, but once you are aware that how the different values, different parameters are stacked together, and how to proceed, then it's very easy. So, and then I think just develop a CAD and then 3D printed. So it's a very easy these days, and for you to see as well. So here again you see, you move and you can see a very good displacement. So I showed it earlier also, but here also it's very clear. So yeah, it can be made out of steel or titanium depending on the requirement, and we can also use for dynamic applications. So suppose maybe 1 millimeter, or even here is a 0.5 millimeter. So for that kind of range, and if it's going for very high speed application, for dynamic application, we can also look at the sigma value for the fatigue failure, and we can recalculate and can see that uh, we can design these kind of things for many experiments, or even for micro actuations. So very good example, and we can try, and you can also try and use it in your applications wherever required. So there are similar requirements. So for instance, if you want to steer a mirror, and suppose if you want to point your lasers to a particular location and want to control it precisely, uh, you can also think of this kind of mechanism. So it's a from the book again, but very nice, and you can see whole flexures here, and but it's based on this principle. So toggling position, you move it, and then so this is getting displaced x, and then you get u, and then therefore you will have this phi rotation. So here what you see here is screw 2 is for course adjustment. So for instance, here you see screw 2s. So if you see, one is threaded on the one frame and the other is threaded here, and as you adjust, what you realize that the entire block is getting lifted. So one is, so if you just push it here, the entire thing will rotate. So, and that's why it's called course adjustment. So it can be replaced with some kind of actuator also. So but manually also you can adjust. So suppose if you want to focus at certain location, so if it's one time, you can use the manual adjustment, but if it's for dynamic application, you can place a actuator and can also do that. What you also realize that the screw 1 here is threaded here, and as you tighten, what you realize that you are pushing this block. So as you push, it's so you can see hinges here. So now you realize that once you push it here, actually you are moving this link. So because it's just like this. So you have a hinge here, you have another hinge, and you are simply pushing it here. So once you push, you are moving this way, and that way you can get X. And because of that X, because it has now moved here, so this can slide. So you can think of a slider mechanism, and then this simply moves in this direction, U. So what happens, it pulls because it's going in this direction. So this will be get pulled, and then because of that, at this point you will have the rotation. So by just moving or adjusting that is screw 1, or you can say a actuation there, you push, and then you can readjust and you can get that phi motion as desired. So it can also work in a closed loop way. So we can have a kind of sensors placed, some PCD, PSD devices, or we can have some sensors at the hinge to measure how much it has rotated, and we can also work in a closed loop manner. So, but this is the basic mechanism one can implement and can get that kind of performance. Again, suppose if it's a dynamic application and no matter even the if the base is moving, but we want to target or target at a certain point precisely, then it has to be a high dynamic application, and we may need to measure the ground vibrations or the vibrations on the vehicle where it's placed, and then accordingly we can adjust and can get very precise motions or the targeting here in this case. So very good use of whole flexures again. There are other application of compliant mechanism, and what we realize that if we want to have some reduction in the input and want a very big ratio, how to achieve that? So we can use elastic adjustment, and a very good example is one of the example. We can also based on this we can design other kind of devices. So for instance, if we have this cantilever, and suppose if we are simply getting this input some deflections, what will happen at x? So if we have this at this point, and if we have this u out here, so u in versus u out, and x and L, that is the ratio. If it's a rigid, we only get leverage, so x by L, that is the ratio we'll usually get. But what happens if it's the because of the bending, it's not rigid body, but it's a deforming elastically and under the bending load. So what happens is to the power 3. So this number is very important, to the power 3, and that's why, unlike any leverage mechanism where it will be simply x by L, a power will be only 1, but here we are getting 3 because of this bending deformation, and that's why we are calling it elastic adjustment. So now if you x by 10 L is 10, now you can imagine that it is to the power 3, so 1000 times. So very big ratio we can achieve, and even a coarse adjustment can give a very fine adjustment if we do in this fashion. So very nice example again, and we can have the coarser adjustment here, but then very fine adjustment we can get because of this elastic adjustment, because of this ratio, and it's a dependency on to the power 3. So again, very good application, and suppose if you are designing conveyors to guide or to transfer very thin films or thin sheets, and these days is very common, and there is a very nice area coming up, and that is large processing area. Large, so it's also called lab, large area processing. So and very thin sheets, and we know that with the sheets, if there is a slight misalignment, things will start going to either one side, or maybe it will just there will be warping and things can go haywire. So we need to have a very good adjustment, and we have to maintain that parallelity. How to achieve that? So once we have what you can see that along one side we can have this adjustment, and the bearing axis here is mounted on a cantilever, tapered cantilever, and if we just adjust it that one, that moves by a very small amount in that vertical direction, and then similarly in the other axis we can do, and again here. So one is moving in this way and the other is moving in this way, and that way we can align that guiding roller precisely. We may the both movement in x and y may not be that important. What is more important is the this angular um, alignments, and this way we can achieve it very nicely. So tilt adjustment of a roller in elastic and plastic deformation. So many times it can be one time only, so it can be plastic deformation also. You can just adjust it and lock it, but it can be elastic also. It can always come back as well. So that's a very good example again. Moving on, there are some flexures, or what we say that when we covered this design for stiffness, we are talking about certain cross section which are torsionally compliant. So when we try to rotate, they can rotate easily, and the stiffnesses are not very high. So we can use those kind of structures also, and those kind of cross sections, and we can get a very good torsion flexures. So again, call a hinge, and it's L strip, L section you have, and now you know if you twist, you can turn it. So if you just place it and apply a torque here, you can get this rotation. What is important to understand that in this case, when you try to rotate, the rotation axis will be the fold axis where the two planes are intersecting. But since all other sides they are moving in the periphery, so it will get stretched, but they will also try to apply the compressive load along that axis. But what happens, since this is not symmetric, because of that loading, it tends to tilt. So we'll get some tilting, and that's why I think it's very important to understand theta will be always coupled by this, and that's why it's very important to have this L by A ratio, length versus this A, the width of the section is very important, and preferably it has to be more than 6. Otherwise we cannot have a large theta, as well as there will be a tilting. So if you want to avoid that kind of things happening, then we have to keep this length higher. So L by A greater than 6. At the same time, of course, we are still looking at smaller deflection, so this theta will be limited. We are not looking for very large deformation. So these things will be valid only for very small angles. So this can be used as a torsionally compliant member. So in order to avoid that tilting, bending over disadvantage, we can use a pair, and then what we can do is we can offset. So you can see that here the base is on one side, and the top plate is on the other side, and actually this part can be removed, so we can get that kind of section, because these are not important, it can be always removed. So this is what you see here. So but even if it's there, it will not do any harm. So if we try to twist, since it's a symmetric, of course after some time the stiffness will be very high, so one may not be able to twist it further, but the bending can be avoided. So again, very good implementation of the concept, and it can be used as a hinge. And again, we this is one example, and we develop a flexure stage with two rotational axes. So we can rotate along the two axes. So you can say x or y axis. So one axis here and the other axis here. So we can have the two rotations. and what you realize that it's stacked, so one over the other. But we may want to have, this is the point of interest, and we want that it should uh, only tilt. So therefore we made sure that the axis they should intersect, and that's why we you see this kind of design. And again, it's a 3D printed, but you can clearly see that when you apply a force which is offset, so you can get all the rotations. So both x and y rotations you can get. So again, very good is for, and the angle of rotation can be really high. So uh, for any kind of application where you need two rotational axis motion, and okay, it can be attached to the actuators, and so if it's at the joint, okay, you can rotate it, but away from the joint you can always have a translation um, movement, or that linear actuators you can use, and you can get these rotations. So again, very good solutions, and yeah, it's a monolithic design. You can also use thin sheet metals, weld it, braze it, and you can get a very good design out of it. So any kind of design, it can be done and tested. So based on the application, if you face any kind of issues, you can always discuss. But what you also realize that you can always apply this principle to make new machines, new devices for your applications. Moving on, if we just use the thin strip sheet flexures, what we are calling, and we know that they are again torsionally compliant members, so we twist it and we can get this deformation. What happens as we twist, there will be a stiffening factor. So the stiffness, so L by B, yes, as L by B is large, okay, that means we can twist it easily. But as it gets shorter, the QT value, the stiffening factor will be very high. And the reason being, as we twist, the outer members, they deform along the cylinder edge or on the surface. So it's more like a helix, but the center line is a fix. So if we initially all the lengths are same, but as we are twisting, the lengths are changing. It means the outer edges will get stretched, and the inner part, the axis will get compressed. So they will start fighting, and definitely because of that, since there is a huge compressive load, there will be warpage, and yes, um, it's also a kind of buckling phenomena, and we cannot use it anymore. So this deflection is very limited. But if we look at it carefully, what we also realize that if we have this strip, okay, we can twist it to some limit, and because of the changing length at the center and the outer edges, we there will be warping, and uh, we cannot use it anymore. But what happens if we remove the constraints what we have in the middle of the section? And this is what we did. And so suppose if we created this part and we created hole, and if we use this member, what we realize that we can twist it more. We can twist to very larger extent, and the stiffness is also get lowered. At the same time, what we also realize, as we twist this L0 versus L, because the outer edges is still same, but since we are allowing it to get shortened, there is change in length, delta L, as we move. It means, again, if we compare with respect to the elastic adjustment, what we also realize here, with the coarser movement in theta, we can have a very fine adjustment along the linear direction. And this is what we propose, and we published it also this year at USPEN uh, in Spain. So we presented, this is one of the work from my PhD student in the lab. So again, very good example, very simple but effective. So it's a modified sheet flexure, what we are saying, and we propose linear to rotary to linear actuating mechanism. So we can get a very fine linear movement with this one. And okay, ball screw is just for comparison. So it has many parts, and but here if we do in this way, and if the requirement is only for few millimeters, it can be very good solution. And it's just a thin sheet metal. So again, very effective. Of course, one has to also remember that it has to be in tension. In compression it may not work. So it has to be always in tension. So we have to find a way to keep it in tension. So this is the comparison. So change in length versus the rotation. So there is rotation theta, and then this is delta L. This blue line is for the strip or sheet, flat sheet flexures. So you can see there is a kink here, and it's basically because of the warpage. So you are not even able to move beyond 70-80 degrees. But as we tested this one, we can almost 3/4 or even full rotation we can get, and we can compare these two. This one is the ideal one just based on the geometry, because it's a deforming in a helix, so that we compare with the modified one. And of course, since there is a preloading, we can always have some straightness, so that's why we see a difference here. But what we realize that it's all elastic mechanism, so it should be repeatable. It doesn't matter whether we are going upwards or downwards. There should not be any hysteresis. So again, means these are the things we can always try in our laboratories, or you can always do it in the workshop or in your labs. And depending on the application, you can use it. So again, a very good example, and we are working on it, and we are getting developing different kind of mechanism, rotary to linear actuating mechanism based on that. There are some more examples, and we can always couple different kind of flexures in parallel or in series, and we can get different kind of flexures with different motions, either rotations or linear motions. So for instance, if we talk about the sheet flexures, we'll have this alpha and beta rotation, so it can get twisted, it can bend, but it will also have this motion. And suppose if we just place this wire flexure, so this is your sheet flexure, this is wire flexure. So what wire flexure does here is it stops this motion, so the vertical displacement, and they, since they are in parallel, what we realize that we only have alpha and beta, so two rotations. Again, just by putting two kind of different kind of flexures, understanding the compliance and the constraint direction, we can effectively put them together and can get a different kind of flexure. So here it will be more like an universal joint. We can also create a elastic ball joint using a wire flexure. So it's this is what we want. So position is fixed, but it should be able to rotate in all the directions, in all the orthogonal directions. So 3 rotations required. So we can use 3 wire flexures, so 3 constraints. But what we realize, because of the geometrical limitations, there is no common pole. So they have to just go beside each other. So the poles are little shifted, little offset. But as we cannot get exact a single pole, but it's slightly shifted. But since again it's a elastic mechanism, we can always characterize and can use it for precision application. So this is the gray body, and we arrange the three wire flexures, and from the other side we can lock with this green body, and we can get a effective elastic ball joint. So moving on, there are very good examples here, and this is the example from University of Twente, and it's also cited in the book. So it's a discentina adjustment, and again flexure based. And what we wanted to have is this theta meridional and azimuthal direction. That adjustment is required, and if we want to point at certain directions all the time, how it can be achieved. So again, this antenna we have, and we can think of a spherical joint here at B, and from B, if we are just simply putting our actuator here, and if we push it, we can get this theta rotation, and in the other direction, if we do this, we can get this psi. So at the at B is a spherical joint, it's a connected, so position is known, and then we have AD and C, those are the actuators. So by changing the length, we can rotate it, and that is the concept. And the implementation here for the B, what you see here is just use 3 wire flexures to create that spherical joint, and then can have these linear actuators here. So servo motors, you have 2 servo motors, and you can orient it precisely. So it's also implemented, and uh, you can see it here as well. So I have seen it while doing my PhD, and there were smaller models also placed in the lecture hall there. So you can see it. So yes, even with the trusses and everything, huge structure, it doesn't mean that you cannot use these flexures. So the dimensions of this flexure not necessarily has to be in microns or in millimeter order, but it can be bigger also, depending on the scale, depending on the load capacity. So even in many air bearing stages, to eliminate certain over constraint, the leaf spring, the sheet flexures are used, but those sheet flexures has a thickness of the order of millimeters. So on the other hand, if it's for some MEMS devices, it can be in microns, and the principles are same, and the way it works is the same, only the scale will be different. So whether it's any kind of MEMS devices, NEMS devices, or whether it's a kind of application, this macro application, it can be equally useful. So Flexure can be used, and many times it's also very easy and effective way to use, because the number of parts gets reduced. The friction is not involved. There is no sliding joint. So the lubrication, the wear and tear, the maintenance, all those things can be avoided. And on top of that, we can get a very good repeatability, and therefore we can achieve higher precision. So we'll stop here. So there are another class of flexures made out of tubes. Again, very interesting and useful. So we'll learn about these kind of flexures in the next lecture, and we'll talk about some more designs in detail, and we should be able to appreciate how these flexures or compliant mechanisms works and how they control different degrees of freedom. So degrees of freedom and constraints together with design of a stiffness, and then we develop different kind of building blocks, different kind of units, flexure units. Many designs, it can be developed ab initio and it can be coupled. Sometimes it can be also assembled, and we'll try to see many such examples, and so that we'll have the confidence to use them effectively for our applications. And with the new push in semiconductor industries, I think we can develop systems and we can support this initiative really well, not just by designing the chips only, but also developing machines to support the front end and back end processes for the chip packaging, for the all sorts of activities related to semiconductor manufacturing. Thank you.